Hello everyone, welcome to Easy BTech. I am Nawaz. I'll be dealing this subject structure analysis 1. In this video, we are going to learn about this degree of static indeterminacy. In this video, we'll start with revising basics of strength of materials. Then we'll see the degree of static indeterminacy for beams, frames, and trusses. So in the strength of materials, you would have learned about the different type of supports. What are those supports is? First one you would have seen about roller support. What is roller support? It is a support which prevent movement in vertical direction. So if you try to prevent a movement in vertical direction, definitely it will cause a reaction. That reaction here is given. Okay. So if a support have only one reaction, that two in vertical direction, then it is known as roller support. Second one is pinned support. So this pinned support, it will prevent movement in horizontal direction as well as vertical direction. So that causing two reactions, that is AX and AY. Then the third type of support which you would have seen is fixed support. This fixed support will prevent movement in all the direction as well as rotation. So causing three reactions. One is AX, AY, EMB. And the movement which prevents the rotation is known as moment. So these are the types of supports. After supports, you would have seen what are the different type of beams. First one is cantilever beam. Cantilever beam is something which in which one direction is fixed, one end is fixed, okay, and another end is free. Whereas the second type of beam is simply supported, where one end is hinged or pinned and another end is roller. Pinned, it has two reactions, roller, it has one reaction. Okay, it is not necessary that the pin should be on left side and roller should be on right side. It can be a mirror image of the same. Another type of beam is overhanging. In this overhanging beam, the beam is projected outwards to the support. So you can see here we have support and beam is projected outwards. So this type of beams is known as overhanging. Next one is fixed end beam. The fixed end beam, both the ends of the beam are fixed. Along with the type of beams, you would also have seen the type of loads. So first one is point load. In the point load, you would have seen that the load will be acting at a particular point of a beam. Okay. Second one is uniformly distributed load. So in this type of load is acted throughout the beam and it is evenly spreaded. Evenly spreaded means at every point of the beam, the intensity or magnitude of the load will be same. Suppose if it here at this point, if it is 0.5, so at each and every point the load will be same, 0.5 Newton per meter or kilonewton per meter. The same, it continues till the end of the beam. Another type of load which we have seen is uniformly varying load. In this type of load will spread throughout the beam, but the intensity won't be same. Here you can see the rectangular direction. It indicates the start of the load is from 0 and end will be at P. P can be anything, that is 2 or 3 or 4 kilonewton per meter. So this load is increasing from one end to another end. This type of load is known as uniformly varying load. After that, we'll take a simple beam which is simply supported beam. This is the simply supported. One end is pinned, another end is roller, and for pinned support we get two reactions, that is horizontal, vertical. In this case I am denoting it with AX and AY. It can be denoted with anything. Okay, and here for roller support, we'll get one reaction that in vertical direction. I am denoting it B. Why? Now I know the number of reactions in this case is 3, and along with that you have seen about the number equilibrium equations. Since throughout this course we'll be dealing with 2D structures, we'll see the equilibrium equations for 2D structure. As per Newton's third law, we'll have three equilibrium equations for any type of 2D structures. What are those? That is sigma fx equal to 0, sigma fy equal to 0, sigma ma equal to 0. What is this sigma fx equal to 0 means? Here x suffix x indicates all the loads in horizontal direction or x direction. If I consider x here, y here, coordinate system, then all the loads acting along the x-axis is known as 0. Sigma fy means same thing. All the loads acting in vertical directions are 0. Sigma ma equal to 0. What does this mean is, so if I take at any point, all the moment acting at that point is 0. Right? Now, we have seen the number of actions generated in the beam, number of equations. I know only the load acting on the beam. I don't know what are the reactions here. To find out, I need to equate all this to the load acting. Okay? This is how we used to solve a problem to find out the reactions. Now, I have known number of reactions. I know number of equilibrium equations. Can I find out the reactions here? Yes, I can easily find out. I don't need any additional help to find out these reactions. So these type of beams where we can easily find out without any additional equations is known as statically determinate beam. And degree of static indeterminacy for this type of beams are 0. Why 0? That is, number of reactions are 3 minus number of equilibrium equations are 3 will give rise to 0. We'll see how to find out this degree of static indeterminacy a bit later. Let us take another example. This example where both the ends of the beam are pinned. This is pinned, this is pinned. Here we'll get 2 reactions, here also we'll get reactions. Now, how many number of reactions we have here are unknowns? We call those are 4. That is Ax, Ay, X, Ay, Bx and By. So total is 4. Right? Now, how many number of equilibrium equations we have? Those are 3. Is this 3 equilibrium equations are sufficient to solve this, find out these unknowns? No. We already have seen in mathematics that the number of unknowns, if we have number of unknowns, the number of equations should be required to solve and get the unknowns here. Here also same case. These 3 equilibrium equations are not sufficient to find the reactions in this beam. And in that case, this beam is known as statically indeterminate. How to find out the statically indeterminate? The number of reactions minus number of equilibrium equations. Number of reactions I have got is 4. Number of equilibrium equation is 3. So 4 minus 3 is 1. The 1 is nothing but degree of static indeterminacy. This indicates additional equations that required to find out the unknowns degree of static indeterminacy. So this will be clear. The degree of static indeterminacy, if I get 1, then I need to get additional equilibrium equation or whatever equation solve that problem. It is similar to the mathematics. Now let us see the different problems on beams, rigid jointed frames, pin jointed frames. Now let us take an example. This is a beam. One end is fixed, one end is roller. This is roller. Okay. Now, fixed. This type of beam is known as propped cantilever. Why it is called propped cantilever is, so if I remove this roller, then this beam will become cantilever. If I just provide some support in vertical direction, it is acting like a prop. Prop in a sense, a support in vertical direction. So that's why I call this one as propped cantilever. So let us see how many reactions we'll get on this end and that end. So for fixed, we know we'll get three reactions: AX, AY, and EMA. Whereas for roller, get only one reactions, B1. Now how many number of reactions I'll get in total? That is 3 is 1 is 4. Number of equilibrium equations we have 3. So what is the degree of static indeterminacy? 4 minus 3. That is number of reactions minus number of equations 1. So I may need one additional equation to find out all the reactions coming onto this beam. This is an example of propped cantilever. Let us look at another beam. So this is a beam. This we call this one as fixed beam. Why? So both ends are fixed here. Right? So for fixed end, we'll get three reactions. Three reaction, that is horizontal, vertical, and moment. Here also horizontal, vertical, and moment. Okay. So the notations, it can vary, but I am following that. I am assuming this is my A, this is my B. That's the reason AX, AY, MB. Here also BX, BY, and MB. Okay. So this is what are the total number of reactions I have? The number of reactions here is 6. How many equilibrium equations I have? Those are 3. The degree of static indeterminacy is nothing but number of reactions minus number of equilibrium equations. So 6 minus 3 is 3. Okay. So for this beam to be solved, to find out the reactions, I may need 3 additional equations. Let us see another example. This is another example of beams. So this is a continuous beam. Here, if a beam has more than one supports, then it is known as continuous beam. Okay. So here at one end I have wind support, another end I have roller support, and another support I have same beam, that is also roller. So these supports can be anything, whether it can be a pin. So it depends on the type of condition. So as you all can see, we have for pin we have two reactions, for roller 1, another roller 1. So total number of unknowns or reactions we get from here is, if I add all this, I'll get 4. And the number of equilibrium equations I have is 3. So now the degree of static indeterminacy is nothing but number of reactions minus number of equations. So 4 minus 3 is 1. So the degree of static indeterminacy for this continuous beam is nothing but 1. So this was some example for beams. Let us go to the frames. So rigid jointed frames. So what are these rigid jointed frames is? For beams, usually we have one member. Okay? And if another member is joined with a joint at any angle, then that is known as frames, rigid jointed frames. So here you can see this is a type of a member here. Okay? And another member is connected at this joint. So it is exactly at 90 degrees. Since two members are connected with a joint, that type of structure is known as rigid jointed frame. Now let us find out the degree of static indeterminacy for this structure. So this is fixed. So we already know for the fixed end we'll get three reactions. Number of unknowns are ax, ay, and ma. Those are three. The number of equilibrium equations are three. So then the degree of static indeterminacy is number of reactions minus number of reactions. So that gives me this is 0. Okay. So this is statically determinate frame. So with the number of equilibrium equations available, we can easily find out the reactions for this frame. Let us see another example where for the same frame we have a support at other end. So now this is fixed, this is roller, and these are here for fixed end we get the number of reactions. For this roller we will get number of reactions. So now number of unknowns are 3 plus 1, that is 4. Number of equilibrium equations we have is 3. Now degree of static indeterminacy we get is number of reactions, that is 4 minus 3 is 1. So this frame is indeterminate structure of static indeterminacy of 1. Okay. Next, let us see another example for jointed frame. So here you can see there are two vertical members and one horizontal, where two ends are fixed support, and here we have two joints waveframe. So number of reactions will be 3 here, 3 here, right? So number of unknowns we'll get here is 6, 3 plus 3, and number of equilibrium equations is 3. Now the degree of static indeterminacy is 3, 6 minus 3 is 3. So this frame is statically indeterminate, the degree of 3. So this was easy part. Now when we have a frame like this, so what's the case? How do you find out the degree of static indeterminacy? It is similar to what we have done in the previous problem. That is, we have three reactions here. Okay, we have three reactions. So we'll apply the same formula. That is 6 minus 3, 3. So we'll get this degree of static indeterminacy. But this static of indeterminacy is external indeterminacy. Because of an additional member joined here, we'll have internal indeterminacy. What is this internal indeterminacy is? We'll get, you would have seen that these reactions are the basic foundation to calculate the member forces. And to find out the members forces, we need these reactions. But since an additional member we have got here, we are unable to find the member forces at this point for this frame. So it will, because of this additional member, and another indeterminacy will generate, and we need to get that many number of unknowns to solve this equation. Okay, so how to find out this internal indeterminacy is, first we need to see how many closed loops we have. Closed loops, so this is open, so it is not a closed one. But if you see this is the closed loop. It's like a closed box or closed circle. So we need to count how many closed loops are there in a structure. Since in this case we have one closed loop, the internal indeterminacy is nothing but 3 into closed loop. So we have 3, and C is nothing but closed loop. Since we have 1 here, E1 is 3. So internal indeterminacy has a degree of 3. Now what is the overall degree of static indeterminacy is nothing but the external indeterminacy plus internal indeterminacy. So external indeterminacy we got is 3 here. Internal indeterminacy we got here 3. 3 plus 3 gives rise to 6. So 6 is nothing but static indeterminacy for this frame structure. So this was some examples for rigid jointed frame. Let us see the example for pin jointed. So what are these pin jointed frames? Pin jointed frame, we also call it as trusses. So what are these trusses? Trusses are nothing, a structure where the loads are only transferred at joints. Okay, all the loads will be transferred only to joints, whereas the frames, for frames, the load can be anywhere throughout the member. So, but the only difference between pin jointed and rigid jointed is the type of load acting. Now, so consider this truss. We already know here. This is a simply supported truss where one end is pinned, the end is roller. So we have two reactions at pinned end, one reaction at roller end. Now let us find the degree of starting. Similar to the previous problem, for all the trusses, we have external indeterminacy and internal indeterminacy, that is DSC, DSI. To find out that, first let us see what is the external indeterminacy. So how many reactions I have? 2 plus 1, 3. Number of equilibrium equations is 3. So externally it is a determinate truss. So no additional equations are required to find out the reactions. Let us see the internal indeterminacy. The internal indeterminacy is given by this formula, that is dsi equal to m minus 2 minus 3. What is m here is number of members in a truss. So in this case we have 1, 2 and 3 members here. So 3 members are there. A number of joints. So joints we need to consider along with the support. Here we have 1 and 3. So if we substitute that here in this formula, we get 0. That means internally also it is determinate. So this is basically a statically determinate truss. So let us see another example. Consider this truss. So how many reactions? Let us see for external. So both supports are pinned. So both at each support will get two reactions. So the number of reactions or unknowns we get here is externally is 4. Number of equilibrium equations are 3. So now externally, what is the degree of statically indeterminacy? So 4 minus 3 is nothing, 1. Okay. Now let us see the internal indeterminacy. To find out the internal indeterminacy, we need to find out how many members are there. So we have 1, 2, 3, 4, 5 and 6. So this whole member is treated as 1. How many joints I have? 1, 2, 3, 4. So here m is equal to 6, number of members are 6, j equal to number of joints are 4. If I substitute that here, so what's the value you'll get? You'll get 1. Okay. So the total degree of static indeterminacy is external indeterminacy plus internal indeterminacy. So 1 plus 1, 2. So overall this truss is statically indeterminate with degree 2. So that's all for this session. I hope it's clear. If you have any doubts, please leave comment. I will revert you back. Thank you for tuning. Bye bye.